Thank you very much, Scott, for the introduction. I hope people can hear me. I am very delighted to have one in-person listener. Well, together with Scott, there will be two. So that's I'm very glad about this. All right, so I'll be talking to you guys a lot. And everyone remote, if you have any questions, feel free to post them. I think Scott is monitoring the question area, and I will be very happy to answer the questions that you may have. All right, so today I will be talking about controlling the catalysis of CO2 reduction. Now, the first question that you may have is, why would you want to do CO2 reduction? In fact, CO2 reduction is a really interesting reaction because it allows us to make complex fuels, such as gasoline, from renewable electricity. Here is how it works. We're making more and more renewable power through wind sources and through solar energy. And the cost of this renewable power is decreasing quite rapidly. Now, the problem is that both wind and solar are intermittent energy sources. They kind of come about whenever they want. And we cannot really control when they are here and when they are not, because we cannot control the weather. So if we want to use these energy sources in a reliable way, we need to somehow transform the energy that they provide into a fuel or in some sort of way that we can store it effectively. We can do that in a very attractive way by using this renewable electricity to convert carbon dioxide and water into chemicals and fuels. Now, what is behind this reaction? When we do a combustion, for example, in our car, we are taking hydrocarbon fuels and we are oxidizing them to generate CO2 and water. So it's a combustion reaction which releases energy. This is what gives us access to the energy that is stored in these fuels. What we are doing in this presentation is we are taking this reaction that releases energy and we are turning it backwards. We are using renewable power to transform carbon dioxide and water back into useful fuels. And this is really interesting chemistry. Now, the question is, how do we want to do that? And what do we need to control in order to achieve this transformation? At the heart of all of this is we need to be able to reduce carbon dioxide. It's a reduction process. And to do this, we need to master electrocatalytic reactivity. Now, what is electrocatalysis? Electrocatalysis is a method that allows us to use electricity to drive chemical reactions. And here is how this works. We build what we call an electrochemical cell. In this cell, on one side, we have an electrode, which is just some sort of a catalyst material that, under the action of an electrical field that we apply, just using current from a solar cell, for example, using this electrical field, this material is able to rip electrons out of water, thereby transforming water into oxygen. It's an oxidation reaction. Oxygen is wonderful. We can just release it into the atmosphere and we have more O2, which is what we breathe. We then take the electrons that we have removed from water and we push them to the other side of our electrochemical cell, where we have a second material that is able to take carbon dioxide and, using these electrons, transform carbon dioxide into a more reduced product, such as, for example, carbon monoxide, the simplest species that we can make in this reaction. Now, this cell that you are seeing here, it's actually not just generally an illustration of this process. It is actually a cell that I built at the very beginning of my PhD research. And what I did here is I use the best catalyst for ripping electrons out of water and the best catalyst for pumping electrons into carbon dioxide and transforming it to carbon monoxide. And I built a cell that is driven by solar cells. So this electrochemical device allowed me to transform carbon dioxide to carbon monoxide and oxygen using only sunlight. So here we are really using chemistry to store solar energy in the form of chemical species. Now, when we analyze the efficiency of this device, we actually find that only 56% of the power that is generated by the solar cells contributes to this chemical reaction that transforms carbon dioxide. The rest of the energy is being lost. So this shows us that even if we take the best materials that are known to humanity, we can still not get to very high conversion efficiencies. And it indicates that there's still a lot of research to do to drive this chemistry forward. And that's what I'm going to be talking about today. If we want to improve CO2 reduction reactions, to improve their energy efficiency and make products that are more complicated than carbon monoxide, we need to first understand through which pathways carbon dioxide transformation takes place. Let's start with an empty catalytic site here shown as a slab. In a first step, under the action of an electron, carbon dioxide is bound to the catalyst surface to form a reduced carbon dioxide species. In the next step, this species is releases an oxygen atom, forms water, and thereby generates carbon monoxide, which is still bound to the catalyst surface. This bound carbon monoxide can either be desorbed and lead to the production of CO as a product, or it can remain at the catalyst surface where it accumulates and then can undergo further reduction steps and hydrogenation steps to form fragments of hydrocarbons, in this case a formal intermediate, which after further hydrogenation can form methane. So we have a pathway that allows us to use electricity to go from carbon dioxide to methane directly. But we can even do more. Two neighboring carbon monoxide species can undergo an electron-mediated dimerization, leading to a dimer of carbon monoxide, which is negatively charged, which subsequently, after further electron and proton transfers, can form ethylene, one of the key intermediates in the chemical industry. So again, we have a pathway that allows us to use electricity to transform carbon dioxide all the way to ethylene, one of the most important chemical feedstocks. So this reactivity is absolutely fascinating. And in the next 30 to 40 minutes or so, I'm going to tell you how we can influence the reaction pathways that we see here to increase the efficiency of this reaction and also to control which product we are making. Electrochemical reactivity always occurs at an electrified interface, also called an electrochemical interface. This interface is characterized by the contact zone between a solid electrode and an electrolyte material. The electrode conducts electrons, whereas the electrolyte conducts ions. It is at the zone in between these two, when conductivity transfers from electronic conductivity to ionic conductivity, that electrocatalytic reactivity takes place. And if we want to control this reactivity, we need to influence both the electrolyte side as well as the electrode side of this reaction. I will show you the following examples of how we do this. First, I will show you how we can control the rate of CO2 reduction to CO by controlling, by influencing these reaction cycles through ionic liquids. I will subsequently show you how we can modulate the selectivity towards producing carbon monoxide or other products by controlling the properties of the electrode surface. Subsequently, I will show you how we can understand the pathways that allow us to go to the synthesis of hydrocarbons. And finally, I will show you how we can exploit this understanding to control the selectivity of producing either ethylene or methane. All right, let's look at the first example. We consider an electrochemical cell. This cell consists of a silver electrode that is in contact with a non-aqueous electrolyte, an acetonitrile electrolyte, into which we introduce carbon dioxide. We start by changing the electrochemical potential that is applied to the silver electrode surface. We do that by going from the right-hand side to the left-hand side on this plot. We start with less reducing potentials and we go towards more reducing potentials. And as we do this, we see that initially we observed no current, but starting at some point, we start to see the appearance of a negative current. Negative currents indicate that we are transforming carbon dioxide to something more reduced. And when we use a gas chromatograph, we can actually show that what we are making here is carbon monoxide. So again, we are transforming CO2 to carbon monoxide under the action of an electrical current alone. Things get interesting, however, then we add an ionic liquid to this solution. If we add a very small amount, so 20 millimolar of ethyl methyl imidazolium tetrafluoroborate, which is an ionic liquid, we find that the reduction, so the transformation of carbon dioxide to carbon monoxide, now occurs at a significantly decreased driving force. So we need to go to significantly less extreme conditions to transform carbon dioxide to carbon monoxide at even a higher rate. So this is something that had already been observed in the literature when I did this experiment. But the question then is, what is actually going on here? What properties of the ionic liquid make how it to increase the rate of carbon dioxide reduction? So I'm laughing because we have a second guest. I'm very happy when we have guests in here. All right, so what property of an ionic liquid allows us to increase the rate of carbon dioxide reduction? Well, there are a number of options. Somehow, the ionic liquid is acting on the cycle that transforms carbon dioxide to carbon monoxide. And it can do that potentially by taking up an electron and transferring this electron to carbon dioxide, right? The imidazolium could be reduced and then transfer this electron more efficiently. Alternatively, the C2 proton of the imidazolium cation, which is here, could actually help the reaction by providing a proton in the step where we are generating water and carbon monoxide. Or alternatively, somehow the surface species that is involved in the reaction, so the CO2 anion radical, could be stabilized at the C2 position. At least all of these hypotheses have been proposed in the literature. So what I was wondering about was, well, which one of those hypotheses is true? So let's look at the first hypothesis. Does the imidazolium cation shuttle electrons to carbon dioxide? Well, we can test this very easily, because if the imidazolium cation shuttles electrons, we should be able to reduce it at the potentials at which CO2 reduction takes place. So here we can see the curve we observe under CO2 in the presence of an imidazolium cation. If we remove CO2 and carry out the same electrochemical sweep under argon alone, we observe no current at all, which is strongly indicative that the imidazolium cation itself is actually not able to take up electrons. Otherwise, we would be seeing a current. So this excludes the hypothesis that electrons are transferred to the imidazolium cation. So what else is going on? Is it possible that the imidazolium C2 protons act as an acid? Does the imidazolium donate the proton during the reaction? Well, to test this, we can take the ethyl methyl imidazolium with the proton at its C2 position, which is actually slightly acidic, and we can run the voltammetric trace. We see this behavior. So we see a strong enhancement, as we have seen before, in the CO2 reduction efficiency. Now, the question is, what happens if we take this C2 proton away? If it acts as an acid, once we remove this C2 proton, well, we would expect a decreased CO2 reduction rate. But if we do this experiment, where we replace the imidazolium C2 proton with a methyl group, we actually see an increase in the co-catalytic effect of the imidazolium cation. So it seems that the C2 proton is also not necessary to generate an enhancement of the CO2 reduction rate by ionic liquids. So at this point, we are a little bit confused. What's really going on here? Because two of the prior literature hypotheses, a role for the imidazolium C2 proton, as well as the imidazolium cation taking up electrons, have been excluded by our data. So let's see what happens if we change the C4 and C5 proton of the imidazolium cation. If you take this imidazolium cation, which is modified by a phenyl group, you can see a strong enhancement effect in the presence of the imidazolium. But if we methylate both the C4 and C5 position, we actually see an almost complete suppression of the enhancement of CO2 reduction by imidazolium cations. So what could be going on here? Well, during the CO2 reduction reaction, we can actually show using other data from other literature as well as from ourselves that the rate limiting step is the electron-mediated binding of carbon dioxide to the catalyst surface in the form of a negatively charged CO2 anion radical. Well, if you generate a negative intermediate at the catalyst surface, you need to compensate the negative charge that is being generated. And the only species that can mediate this charge compensation is the imidazolium cation. This leads us to propose that the imidazolium cation stabilizes the negatively charged CO2 anion radical at the C4 and C5 position, leading to an interaction as the one that is shown here. Now, what I want to impress upon you here is not that we understand all the molecular details of this interaction, and this is what we continue to research. However, what I can show you is that very fine molecular transformations to species that are present in the solution allow us to modulate what is going on at the electrode surface, and thereby give us a handle to design catalysts beyond the binding site. This is one of the main goals of the Department of Energy Catalysis Research Trust. And we will come back to this discussion in a bit. Let me check the time. All right. So after discussing how we can modulate the rate of the transformation of CO2 to CO through properties of the electrolyte, let's now see what the impact of the electrode material is in CO2 reduction reactions. In fact, when we carry out CO2 reduction in aqueous electrolytes, we are faced with a selectivity challenge. While we can transform carbon dioxide to, say, carbon monoxide at the electrode surface, that's what we have discussed before, we are now in the presence of water. And another reaction that can take place is the transformation of water and protons to molecular hydrogen. But if we want to reduce CO2, we want to avoid this side reaction. So let's see how we can do this. We started our investigations by looking at copper oxide-based catalysts. Now, these catalysts are very interesting because they have some, they show a particularly interesting behavior. When you reduce copper oxide-based catalysts to metallic copper, you obtain one of the most active catalysts that is known for CO2 reduction reactions. And this catalyst can not only make carbon monoxide, but it also produces ethylene, methane, a lot of different alcohols such as propanol and ethanol, other oxygenates, and copious amounts of hydrogen as a side product. Here is how this catalyst looks like. Now, when working with these systems, we discovered something very interesting. This was a serendipitous discovery. When you use atomic layer deposition, which is a very precise method for modifying surfaces, to deposit very thin layers of tin oxide on copper oxide, leading to quite uniform deposition of tin material. Once you reduce this material, you get some sort of a reduced tin-coated copper catalyst. And what is very interesting is the behavior of this catalyst in CO2 reduction reactions. So let's now see. When we look at the copper catalyst derived from the reduction of a copper oxide material, we can see that it produces almost no carbon monoxide. So here we look at the production rate as a function of the electrochemical driving force. And we see that we have almost no production of carbon monoxide. While at the same time, as we go to higher driving force, we get copious amounts of hydrogen. So I would say that this catalyst is pretty good at making hydrogen, but it is really not that good at reducing carbon dioxide. If we introduce only 2 monolayers of tin at the surface of this material, the selectivity changes drastically. We can see a strong onset in carbon monoxide production at already relatively low driving forces, while, and this is really striking, the production of hydrogen is strongly suppressed. So by only slightly modifying the surface of our catalyst, we're able to completely change the outcome of the reaction, going from a material that makes hydrogen to a material that makes CO with high selectivity. So this leads to the question, what is actually going on here? What is tin doing in our material? Well, we can actually measure the impact of tin on the adsorption of species on the catalyst surface. This is quite diagnostic. If we record the adsorption isotherm for hydrogen, which is one of the key intermediates in the generation of molecular hydrogen, we can see that modifying the catalyst with copper and tin decreases the binding strength of hydrogen. And equally, when going from pure copper catalysts, when we look at the binding strength of carbon monoxide, we can see that the affinity of CO is equally decreased as we introduce tin into our catalyst surface. So what is the impact of this on the catalytic reaction? Well, we can look at this by considering the reported hydrogen evolution activity as a function of the binding strength of hydrogen. When we start with copper and move towards lower binding strengths of hydrogen, we can see that we expect the activity for hydrogen evolution to decrease. And this is indeed what we are observing. This is due to the fact that we are now decreasing the efficiency of the hydrogen evolution pathway. When we then look at the reported activity for CO2 reduction as a function of the binding strength of carbon monoxide, which is the key intermediate in CO2 reduction, we can see that starting from copper and going towards decreased binding strengths of CO, we expect to increase the rate of carbon dioxide transformation. This is due to the fact that we are weakening the surface affinity of CO, which more rapidly releases CO and thereby liberates new active sites, which can be used for transforming CO2. So essentially, we have, through a minute modification of the surface of copper, succeeded in transforming a material that is totally unselective, that makes a little bit of CO and plenty of hydrogen, into a material that produces carbon monoxide with high selectivity at all the driving forces we apply. And which is, by itself, entirely earth abundant. This was the first time that the truly earth abundant material have been demonstrated that is highly selective for producing CO. Now, using this material, we can actually make a step forward in transforming CO2 to useful products. Remember this cell? This is what I showed at the very beginning. We used this cell to transform under the action of sunlight, carbon dioxide to carbon monoxide and oxygen. And actually, with this cell, using iridium oxide and gold, so the most expensive material imaginable as catalysts, we achieved a 6.5% solar to carbon monoxide energy conversion efficiency. Using now our new tin modified copper catalyst, which is entirely earth abundant, and driving it with sunlight, we were able to set a new world record to transform solar energy to energy stored in carbon monoxide with 13.4% efficiency. And this record stayed for quite a long time. It has recently been broken, but I'm still quite proud of it. All right. So far, you have seen how we can modulate properties of the electrolyte, as well as properties of the electrode surface to control the rate of CO2 transformation to CO, as well as the selectivity between the generation of CO and the generation of hydrogen. But what I was discussing at the beginning was that we actually want to make hydrocarbon fuels. So let's now see what we actually need to do to transform carbon dioxide to hydrocarbon fuels. When we look at the catalytic cycles that take CO to ethylene and methane, as they occur on copper catalysts and only on copper catalysts, we can see that we actually already know from previous literature what kind of intermediates are involved in the production of ethylene and in the production of methane. But what we do not know is how these intermediates are being produced. But it is knowing how these intermediates are being produced that allows us to control the selectivity between the different products. So how do we generate insight? Well, one way is for us to use a kinetic analysis. Kinetic analysis means we measure the rate of production of all the different products. Hydrogen as a side product, ethylene as one of the desired products, methane as another desired product, as a function of the parameters of our catalytic system. In this case, the electrochemical driving force E and the partial pressure of CO. From carrying out these measurements, we can learn a lot of mechanistic information into how these transformations that lead from carbon dioxide to the production of hydrocarbons actually take place. It turns out that these measurements are really not simple. We cannot just go into an aqueous cell, classical electrochemical cell, and carry those out. This has to do with the fact that carbon monoxide has very weak solubility in water, which is commonly used for these reactions. So what we do is we build a model system. We are working at minus 35 degrees Celsius in an ethanol-based electrolyte, which allows us to achieve very high solubilities of carbon monoxide and, for the first time, get very detailed data on the transformation of CO2 and CO to hydrocarbons. So let's look at this data. Let's start at looking at the synthesis of methane. We are considering a copper electrode that is in contact with an ethanol electrolyte at minus 35 degrees Celsius. We are introducing carbon monoxide into this electrolyte at a very well-controlled pressure. And as we start applying a reducing potential to this copper electrode, we start to observe the production of methane. Now, if we plot this methane production on a logarithmic scale as a function of the electrochemical driving force, we can see that we get a linear curve. Now, the reason why this curve is linear has a lot to do with how electrochemistry activates reactions. In fact, electrochemical processes follow nothing other than the Arrhenius equation, which is simply modified by an electrochemical term. And in this electrochemical term, there is a parameter alpha that contains a lot of mechanistic information and that allows us to understand how the electrocatalytic synthesis of hydrocarbon works. All right, so let me check the time. Okay. So I'm going to show you two specific cases now of how we can apply our insight into the parameter alpha to understand reaction mechanisms. Let's consider a reaction where we take a substrate to a product. And this reaction involves a rate-limiting electron transfer. In this case, the reaction follows this free energy diagram. We have a substrate and an electron going through a transition state to a product. As we now increase the driving force in this reaction, we are moving up the initial state energy because it contains the electron. And now we get closer to the energy of the transition state. So we would say that the activation barrier of this reaction, which is essentially the difference between the initial state energy and the transition state energy, would decrease, right? But it is not so simple. In fact, since the transition state itself also carries a certain charge, it too will be impacted by the electrode potential that we are applying. And the transition state energy will also increase. As a result, not all of the energy that we are introducing into this system will end up changing the activation barrier, only a small part of it. And the part which modifies the height of the activation barrier is what we call the transition transfer coefficient alpha, which in this case will always be smaller than 1. So that's very complicated, but it's getting even more complicated. Let's consider the following reaction sequence, where we start with a substrate that undergoes an equilibrium electron transfer to an intermediate which is then followed by a rate-limiting chemical step to a product. Here, we have the following free energy diagram. The substrate and the electron goes to an intermediate, goes through a very large transition state energy for a purely chemical reaction to a product. As we again increase the driving force of the reaction, so pushing more reductive electrochemical potential, the initial state energy increases. But in this case, since the rate limiting step is a pure chemical reaction, its energy will not be impacted by the electrode potential we are applying. And as a result, the activation barrier between the new initial state and the transition state will simply be the difference between the original activation barrier and the change in the applied electrode potential. So as a result, all of the energy that we introduce into the initial state will end up changing the height of our activation barrier. Okay, so this is all very theoretical, and I think many may not have followed, but that's not a problem. Because knowing these limiting mechanistic cases and how they change the value of the transfer coefficient alpha, we can now start extracting alpha from our experimental data. We can do that from the slope of this curve. And when we do that, we get that methane is produced through a transfer coefficient of 1, which is curious because it tells us that methane is produced in a rate limiting step that is entirely chemical in nature. But we are doing electrochemistry. And our data tells us that the rate limiting step is a chemical reaction, no electron transfer, nothing. So how is this possible when we do an electrochemical reaction? So here we are having some sort of new insight. So let's dig in a little bit more. If we start changing the pressure of carbon monoxide that we introduce in our system, we observe something interesting, which correlates with our original finding. As we go from low pressures of CO to higher and higher and higher and higher pressures of CO, we can see that at a constant driving force, the rate of methane production decreases as we increase the amount of CO in our system. But this is surprising because carbon monoxide is the substrate leading to the production of methane. So the substrate is suppressing the production of its own product. Using this data, we can gain quite interesting mechanistic insight. In fact, if we look at the different pathways which lead to the production of methane, using the two observations, namely that the rate limiting step is purely chemical in nature and that the increasing amounts of CO suppress the production of methane, we can find out the chemical nature of the rate determining step of this reaction. We know from previous literature that the key intermediate that leads to the production of methane is a surface-bound CHO group. Now, this CHO group, interestingly, can be produced in two different ways. One way is a reaction between a surface-bound carbon monoxide species with a proton donor in solution. This is an electron-mediated reaction. Now, if this reaction were taking place, the more carbon monoxide we have on the surface, the faster the reaction should proceed, until it reaches a plateau when we have saturated our surface completely with carbon monoxide. Furthermore, this reaction involves an electron transfer. And our data tells us that the rate limiting step in producing methane does not involve an electron transfer. So both the impact of carbon monoxide, which we would expect to at most lead to a constant reaction rate, and the rate limiting electron transfer here, both indicate that this is not the mechanism that produces methane in our reaction. But luckily, there is another pathway through which we can form a surface formula species. And this is what we call a Langmuir-Hinshelwood reaction between a surface-bound hydrogen atom and a surface-bound carbon monoxide species. So let's see how this reaction behaves as we change the amount of carbon monoxide in our reaction. So as we have very little CO in the system and we introduce more, the reaction rate increases. But as we are now adding even more carbon monoxide to the surface, since both surface-bound hydrogen and surface-bound carbon monoxide is required for the reaction to take place, once we replace the surface-bound hydrogen by carbon monoxide, the reaction rate will go down. That's characteristic for a Langmuir-Hinshelwood reaction. And actually, in Wisconsin, this was discovered independently by Haugen and Watson. And so that's why we call it Langmuir-Hinshelwood, Haugen-Watson in Wisconsin. Furthermore, what you are looking at here is a pure chemical reaction. There is no electron transfer required for producing a fermion species from a surface-bound hydrogen and carbon monoxide compound. And as a result, based on our data, we can propose with quite a bit of confidence that the rate-limiting step in producing methane from carbon monoxide is the surface reaction between a bound hydrogen and a bound carbon monoxide species. Hydrogen and carbon monoxide are in competition with each other for binding sites, explaining why the rate of methane production decreases with increasing amount of CO in the system. And now the question is, well, what does the electrochemistry do here? Well, the only thing electrochemistry does here is generate a surface-bound hydrogen atom, which is one of the species that contribute to the chemical reaction, which then makes up the rate-limiting step. All right. That's the electrochemical step. I think I should probably get to the end, right? All right, so I'm going to skip a few things here in the interest of time. Interestingly, when we look at the impact of the carbon monoxide pressure on the rate of ethylene formation, we can see that the ethylene production rate remains the same for all carbon monoxide pressures. And our data also tells us, which actually indicates that the sites which produce ethylene are saturated at all the partial pressures that we can reach in our system. And we observe a transfer coefficient of 0.5, which is smaller than 1, which, if you remember my whole theoretical development, indicates that ethylene is produced in a rate-limiting electron transfer reaction. All right. So this leads to an overall picture for the impact for the mechanisms that lead to the production of methane and ethylene in carbon dioxide reduction reactions. I now have additional data that allows us to show how we can exploit this impact. These mechanistic pathways to control the selectivity between methane production and ethylene production. But in the interest of time and potentially also people who have to go to other courses afterwards, I will skip this for now. Let me get to the conclusion. All right. So here's what I would like you to take away from it. Electrocatalytic reactions take place at the electrochemical interface, which is defined by the contact between an electrolyte, which is an ion conductor, and the electrode, which is a electron conduction. Both of which, the properties of both of which are equally important for controlling the rate and the selectivity of electrocatalytic reactions. I've shown you how we can control the precise molecular structure of electrolytes and electrolyte additives to control CO2 reduction reactions. I've shown you how we can use precise modifications of the surface of electrode materials to control the selectivity of CO2 reduction reactions between the production of hydrogen and carbon monoxide. And I've shown you how we can use fundamental mechanistic insights to understand how the competition for active sites between H and CO controls the selectivity for the production of methane as well as ethylene. Now, very briefly, what does our group do here at the University of Wisconsin overall? Essentially, this is our mission statement. I will read it. The Schreier Group aims to understand the fundamental processes which govern catalysis at the solid electrolyte interface to expand the scope of chemical reactivity that can be driven by electricity. So we use all of the knowledge that I have shown you so far to find ways to use renewable electricity to drive complicated reactions such as they occur in the chemical industry, forming carpets, tires, tissues, cosmetics, fertilizers, paints, plastics, and fuels. And we are currently in the position where we are looking for postdocs. We will be taking up on PhDs this fall, and we have open undergrad positions. So feel free to write to me to mschreier2@wisc.edu if you want to join us in this effort. All right, with this, I'm very happy to answer any questions you may have. So let me repeat your question as well as try to reframe. So what you're asking is, you say you have heard that there are photoelectrocatalysts which can produce hydrogen. Yeah. And you're asking if this work is related. Is that correct?
If there's also ways that can be done for
CO2 reduction.
Yeah.
Okay. So, this is a fantastic question. I really like it. There's a lot of history to this question. When I was a graduate student, and none of this work is shown here, I actually started working with photoelectrocatalytic systems. Pretty much photocatalysts. This showed relatively low rates of transformation. And my PhD advisor, Michael Gretzel, he always told us, like, why don't you just make catalysts and connect them to solar cells? Okay? And we resisted. We always told him, like, but photoelectrocatalysts are really interesting, and photocatalysts are very interesting. And he was like, why don't you just connect those together? And then we were like, yeah, why actually not? And so we tried doing this, okay? And so that's how this example came about. I used the best oxygen evolution catalyst. I used the best catalyst for reducing carbon dioxide and connected it with 3 solar cells. These were actually perovskite solar cells, the hottest solar cell type right now. And this led to the world record, 6.5%, published in Nature Communications quite a while ago, 2015, right? And so this is actually how this came about. In principle, you can do these reactions on photoelectrodes, you can do these reactions on photocatalysts, and there's a lot of work that has been done. But to explore a novel avenue, which is kind of tangential to photocatalysts and photoelectrodes, we went and we did these tests to just see, like, hey, what kind of efficiencies can we achieve? And it led to the project. So the answer is yes, you can do all of this. And actually, my work started in this direction. But then we moved much more towards the design of electrocatalysts, where I found them my big passion. Okay. Does that answer your question?
Yeah. So just not efficient then?
The efficiencies are generally a bit lower. Stabilities are also a little bit lower. But there are application cases where photocatalysts as well as photoelectrodes are interested.
Question online here, I think it was kind of at the beginning, yeah, why specifically renewable energy to do the electricity, not other forms of electricity?
That's a very good question. Let me go back here. So this whole scheme only makes sense if we use renewable electricity. The reason is the following. If we were to use electricity that is produced, let's say from burning gasoline or burning natural gas or burning coal, why would we want to make hydrocarbon fuels with the energy that is generated when we burn these hydrocarbon fuels? So essentially, we would just kind of close this cycle and go in the cycle all along, right? We would take CO2 and water, we would burn fuels, we would use this to remake fuels, and then we would burn them again to drive the cycle. So it would not make much sense. So this approach is a very attractive technology to store renewable energy. Because renewable energy is so intermittent and we need to find ways to store this intermittent power. That's where this chemistry and technology can really shine. Because in contrast to making hydrogen, right, as you have seen that many people do, or in contrast to storing energy in batteries, here we are making a fuel that is extremely energy dense, extremely easy to transport, extremely and can be extremely well stored, all of which is not the case with hydrogen and battery technologies. Then people may ask, well, why don't you use nuclear power? That is a different question because there may be other avenues to convert nuclear power to chemical fuels that should also be explored. So that is something that one would have to look at from a techno-economic side if it would make sense.
And maybe as well, so the techno-economic side, a lot of times if you build a big plant to make this, you will want to utilize it as much as possible. So is there an issue with the intermittency of renewable energy and being able to kind of utilize that capital investment to create these fuels?
That is a very big question, right? Because this technology is not yet mature. There's progress being made. There are startups that are making true progress, but overall the technology is expensive and you're trying to convert intermittent energy. And so you are underutilizing your capital investment. So the only way I see this turn into a commercial application is if we are really able to reduce the cost of the system as much as possible, right? And my work where I use tin to modify copper surfaces to make a highly selective catalyst, which is entirely earth abundant and comparably cheap, goes into this direction, where it's actually making a material that is fairly cost effective compared to gold and silver, which are commonly used actually as catalysts in these applications, with the goal of reducing the cost and finding and thereby enabling this application.
More questions on here. Are there other hydrocarbons that you can make?
We would love to. We would love to. We don't have the time right now, but when you look at the mechanisms that I showed, actually the pathways go towards methane and ethylene very early in the reaction. So it's really going into these two directions. So currently we do not have many other products in terms of hydrocarbons that we can make. Ethylene, however, is very easy to transform. So we can envision schemes where we make ethylene and then transform it into many other hydrocarbons. But directly electrochemically making other hydrocarbons is not something that has been achieved, with the exception of a couple of other species, which I can list. We can make ethane. It's very simple. We hydrogenate ethylene in the same cell. We can also make ethanol. So we can make like alcohols. We can also make propanol. It's kind of interesting why we make propanol, but then not propane. But that has also mechanistic reasons. And we can make formic acid. And then there are a few minor products, but in terms of hydrocarbons, we're making methane and ethylene.
Another question. Could you say anything about how this technology might lend itself to capturing atmospheric carbon and then converting to renewable methane?
Yes, absolutely. That's the dream. So there is a big conversation going on in the community. The conversation is, where is the CO2 coming from? Like, I have strong opinions on this topic because I see that getting the CO2 is the big challenge, right? If you want to capture the CO2 from a plant where you are burning fossil fuels, we come back to the same question: should we use fossil fuels to reduce carbon dioxide, right? It doesn't make sense, right? So then people say, well, then let's just take it from a cement plant where CO2 is under high concentrations. But then why don't we make cement less CO2 emitting, you know? So the question really is, where does the CO2 come from? My personal opinion is the CO2 needs to come from the atmosphere so that we can achieve a truly closed cycle. CO2 and water, those two fuels, goes back to CO2 and water. So for this cycle to work, we need to capture CO2 from the atmosphere. Now we can do CO2 capture electrochemically. And then we can envision, like, can we somehow integrate this? But that is a little bit further out. My answer to this question is essentially that the cycle assumes that I've shown here that we capture the CO2 from the atmosphere. And what I have discussed today are fundamental mechanistic pathways through which we can convert this carbon dioxide to more useful products than fuels.
Any more questions here? We're out of time, but thank you so much for your presentation, for answering the questions today.
Thank you for having me. This was very nice.
All right, and for those of us joining online, we are taking a break for spring break. We'll be back with the next presentation March 21st. So hope to see you all then.